Good morning. Welcome to Chapter 3, Name, Scopes, and Bindings. Overview of name, scope, and bindings. Name, scope, and bindings. A name is exactly what you think it is. Most names are identifiers, symbols, plus can also be names. A binding is an association between two things, such as a name and a thing in names. The scope of a binding is the part of the program textually in which the binding is active. So basically right here, we are talking about the name of a variable and the binding for that variable. And the binding is an association between two things. Usually is the name and it's the thing it named to. So basically, for example, we have a integer a, and then it actually binds to a memory location, and then we can put the data over there. Or we have object type B, and that B actually refers to an object or certain data field. So that is the binding between the variable and the object that is associated with, or the memory location with the variable that is associated with. That relationship is the binding. And when the binding is active, we call it is the scope of the binding. So the name John Smith, maybe this guy bind to a soldier, or a cosplay player, or a office man, or a basketball playing kid. So the name can identify different person of different characteristics. And the binding is the association between the name and the object. Name, scope, binding. Here I show you the name, scope, and binding for some programming language. And this we can call it the programming language memory model. And this is very important. Before you study some language, you actually know about the programming language memory model, because usually the name is bound with some memory location, and that is the binding. So this example is actually given for Java. We have the visibility modifier, we have the global and local issue, we have static and instant members. These are different issues related to name, scope, and binding. So let's get started with the scope. The scope, we have the lowest level, block level, or loop level, functional level, or parameter list. These we usually call all of these the local variables. And local variables are usually stored in the stack or call stack of a function. And usually each thread has its individual call stack. And you may have a program counter associated with that call stack for return purpose. And the variable may belong to certain module or certain class. Usually you call it as instance variable. And it may be a static variable that being put into the method area or global context area. That's actually for this static variable. For the instance variable, usually is stored in the heap area. So instance variable should store in some heap. and heap is not shown over here. And static data actually is stored. It's over here, but actually is pulled up over here. And then the static data actually is shared by every instance. We can also call it as class variable. It's stored in this method area or constant area, and also for the intern string. What is intern string? Intern string is substring that being included in double quote, such as this W words. Here, I give you the example of the binding. For example, I have a program, main program, and that actually call a constructor student with a parameter type of integer and string. Then this student constructor call a setName, and that setName function with a parameter of the string type. So right here, my main program may have a student object for reference S. For example, in my main program, I may write something like this. I may write student and S equals new student. In that case, I call it constructor in Java language, and this one actually it will create an object in the heap, and the object will return, and the constructor will return. Actually, not return. Actually, it will be actually through this assignment after new assigned to S. And we know the constructor have no return type, so I shouldn't call it as a return type, but technically it's the result for this new function. And new is similar to the memory allocate in C language or C allocate in C double plus C language actually. So the address of this object, such as 53A5 or hash code, will be stored into that S variable. And the integer number of students, maybe 13, will be stored in here. And here instead, we call this as a call frame for the main function. So this number of students and the S inside of main function, we call it the local variable for main function. It is pushed into the call stack and put in this call frame over here. And when we call this student constructor, inside the student constructor, we have a parameter for age and name, and those are considered to be a local variable, even though it's on the parameter list, but it will be put into the call frame as well. And a implicit declared this reference will be pointing to the same object as this S is pointing to. And this one is implicit because you don't need to declare it, and it is existing over there for this reference. And then this student constructor may call a setName function, and setName function actually has a string parameter. And that string parameter, for example, is this name. It will store again another address that for the string John. And here actually it's actually mean it is called by string, created by new string and John over there. It will store that into the heap. If it is not called by, actually this string is not created by new string, instead it is created by John, a intern string, then that string will be stored in the constant pool, as we shown in the previous chart. as we shown right here, the intern string. Sorry, the intern string over here. That is actually in the non-heap area. If you use the double quote John. So this one actually, the object for the string is actually using the new string to create a new string object in the heap. So this chart shows you the name, scope, and binding. And scope actually is where the variable exists. So when this setName function finish, this variable name is done. It will be popped out of the state. So basically, these are gone from the stack. And then when we finish the constructor, these are gone. So these, we call it as local variable. Name, scope, and binding. Binding time is the point at which a binding is created. So for example, the new constructor actually will create a binding between the reference variable and the object. And when you declare a integer a, it actually not allocating any memory for it yet. For example, you have an integer a and then semicolon. This one actually is not bound yet. Until you have this a equals 3, then actually you allocate a constant 3 and assign it to a. That binding created by the assignment. So binding time is the point at which binding is created, or more general, the point at which any implementation decision is made. So basically you have several different timing for creating the binding, but the binding is something like this. But the creation of the binding actually can be language design time, program structure, possibly type, or it can be a language implementation time to decide the binding. So basically, it's talking about something like dynamic binding or static binding, those type of things. When you implement a language or the language design, you decided the binding time. So here we talk about the static binding and dynamic binding. These are defined by at the language design time or implementation time. We have static binding. Static binding when the compiler can determine which method in the class hierarchy to use at a particular object. So for example, there is no polymorphism involved, the compiler will use the static binding. And when there is a polymorphism involved, you need to call a polymorphic method, then the dynamic or late binding will be used. For example, right here, if a geometry object, we may have different version of the area. And the geometry object maybe is a circle, maybe a rectangle. The area is different. For circle, it's pi r squared. And for rectangle, it's actually height times width. So the definition of area is different. So when we had a polymorphic object X pointing to maybe a different geometry object, and that geometry object actually inherited by circle and rectangle, we cannot decide it at the compile time of which function we will run. Then we will use the dynamic late binding. But if the object is tied to a circle that's clear and no confusion, then we can actually call the area function definition by the circle class. And the compiler code will determine the method to be used in the class hierarchy. And we call this early binding or static binding. And here we have different things, the parametric binding and the polymorphic binding. Let's talk about this polymorphic method binding first, because this is related to dynamic binding. So right here we have a colored point P, and a new colored point 10, 20 is the X and Y, and also color red. Color red is a constant, so it's fine. And then this class object actually is an instance of the class, a colored pointer class. So right here, the class is attached to this class. And then it can run getColor and getX. GetX, actually, the function may be defined in the point class. And this colored point just inherit the power point class. So you actually get a definition from the point class. If your class doesn't have the definition, you'll go up to search for your superclass for the definition of the functions. And instead, the get class is defined by your own class. So you will find the local copy defined in your class to run this get color function. And if there is different implementation or definition by point class, we will still be using this get color version in your colored point class. That's a rule for dynamic binding. You will find the implementation of a function in the dynamic binding chain, and whichever class is closer to you in the inheritance hierarchy, you will use that version. And that's polymorphic method binding, or we call it dynamic binding. And parametric binding is talking about the pattern matching, and the pattern matching actually is used for the static binding. So this is related to overloading, not overriding. Overriding is related to dynamic binding. And overloading, actually, when you call a subroutine, and you will check the subroutine or function of different signature. So basically, you will check the type. So maybe you have an integer, and string. And then there may be different subroutine implementation. There may be an integer, string version for that subroutine. There may be is another version that is double string version. And then when we call, we will find the right version for you by the parameter matching. And this is binding, and we call it parametric binding. And usually it's related to the overloaded function, not overriding. Overriding will go to this dynamic binding. So this overloading function, when we match it, actually it is a static binding method. At the compile time, we can determine it already. And this dynamic binding, polymorphic method binding, will have to wait until your class being called, the object being called, and then we determine whichever version is closer to it. So parametric type binding, this is yet another issue when we have a generic data type. For example, like we have a array list and then put a integer or a string over there. That is a array list with type variable. So this T over here, when we talk about this my generic box with type T, that T actually is called the type variable, and type variable will be matched. And when will this matching happen? It actually will be matched at the compile time, not the running time. So at the compile time, we actually will actually match the T type, and then actually the T type will be determined, and then we will determine which object, what type of object we are actually calling. So that is a type variable, and type, we call this T as type parameter, and type parameter usually will have a definition right here. When we actually use the constructor, we will have to assign the type parameter over there. So this generic function or generic definition will have generic class, generic data, and generic method, three different generic stuff to be studied. Okay, here is the C++ namespace. For C++, you have a namespace, and the namespace maybe also is defined or using other namespace or info from different namespace. So you would have to check when you call a function, you have to check the most closer namespace to your function. For example, I have a SD and a var variable, and then in my namespace stats. And that states actually my function actually call is namespace, and that namespace is imported, and that imported namespace will actually reference to the base namespace, and base namespace will go to the global environment variable setting, and then find certain package and assign those definition for the variable we seen in the namespace stats. So here show you the binding hierarchy for the namespaces when you see a C++ language. C++ virtual function for dynamic binding. The C++ virtual function is the dynamic binding or polymorphic method used for C++ language. And actually, the definition of virtual function is quite different from the dynamic function that is used in Java. So it uses a virtual table or V table for the different definition of a same function name and signature for the overriding purpose. So we have a base class, we have a derived class for base class 1, and we also have a base class 2, and then we have a derived class 2 object for the base class. And this base derived class object 1 and 2 actually have different definition for the show function. And the show function actually need to, you will find the implementation by the V table. And we call this as a virtual function. A virtual function actually is the same with Java's polymorphic method. And those polymorphic method got its definition at the runtime. We call it dynamic binding. And similarly for C++ virtual function. We have a virtual table. It's a table contain the address of virtual function for each class. So we will be able to find them at the runtime. So for C++, the virtual function actually is defined by the programmer, not by the language itself. Because the vtable virtual function have to be explicitly defined as the virtual function, and the virtual table vtable will be created. And vpointer is actually a entry in the virtual table, and that actually pointing to the entry, a certain entry in the vtable, so you can find where the virtual function is. So now let's look at the binding. The notion of binding time, we have static binding time, and in static binding time we have language design time, language implementation time, program writing time, and compile time. So binding actually, when it happens, has different timing, and here we have 4 different static binding time. In most language, the control flow construct the set of fundamental primitive data type, the available constructor for creating the complex type, and the many other aspects of the language semantics are chosen when the language is designed. So these different features like if, then, else, those kind of things actually is developed at the language design time. Most language manuals leave a variety of issues to the discretion of the language implementer, Typical example including the precision of the number of bits. So this actually is defined at the implementation time. Java is actually not a good example because Java is officially of the same size for different platforms and different implementation of the compiler. But for C, C++ language, in the old days, actually, different platform like or even different vendor of the compiler have different definition for the number of bits for even for integer. So that actually is defined at the language implementation time. And sometimes like this virtual function assignment is defined by the programmer. And for the choose of algorithm, data structure, and name. And compiler choose mapping of high-level construct to the machine code. And this is a compiler time for binding time. And including layout of statistically defined data in memory. The notion of binding time, when we talk about dynamic binding time, actually is not only one time. It can be the link time, load time, or run time. So actually, it also related to how you compile your program. Are you using the compile link go structure, or you use the link go and link go, load go and link go? It's more like Java virtual machine where you load the class first, and then you try to run it, and you will actually call the just-in-time compiler. So you link the program and then find the right function you want to use and then go. That's called load go and link go. And here are 4 different compile process for different language. Let's look at the JavaScript first. JavaScript has the DOM, document object model, and it's the HTML code pass it and then generate a function and its data type. Okay, so those is a binding between your tag and also your object model, and that's determined when you compile the JavaScript. And JavaScript compilation actually is done at the web engine. So actually, you finish the compilation, you already know those what are those tag means. It will link back to the domain document object model, and then we link, and then actually there's nothing to say. It's a compiling, and then you can actually run for that function and then get certain definition for that JavaScript. So JavaScript is a simple interpreter or script language. So it actually follows the compile link go process. And then C++ and Ada, it used a complicated flow, but in the old day, it also followed the GCC compile link and go flow. And Java model is different. Java model is using the load interpret link just-in-time compiler and go, the load go and link go structure. So you load your class, you compile your class to a class by file. So we get that prepared, and after that we load the class into the Java virtual machine, and then we actually try to run it when it is called. And at that time we do just-in-time translation. Actually, it is interpreter, and then we link or bind your function that is needed for dynamic binding, and then we run the program. So this is a load go link go structure. And C# and the .NET package has dual compile process. It can be a C# for C# itself. It can be just like Java's flow, similar flow. But Visual C++, actually it had compile link go, compile link and compile, or compile, actually source code compile. You know, it has different way. For example, you can compile to dynamic link library, and then at the time your source code is compiled, you link with those dynamic library, or you can just compile your source code into the executable file. Implementation decision, runtime. Runtime, you have variable value and variable binding, size of string and array, static heap or stack. This kind of different decision to be made. And subsume the following things. These are the procedures. Program startup time, that's a load time. Module entry time, that's use time. Elaboration time, a point at which declaration is first seen. That actually is the declaration time. And procedure entry time, that's called when a procedure is called. Block entry time is actually when the block is run over. Statement execution time is the execution time of a certain statement. So these are different timings of different in a program. And then it actually all depends on how the language is implemented to get to this different time for binding. So name, scope, and binding, the terms static and dynamic are generally used to refer to whether static is usually a cost term, or sometimes we refer to a compile time or any time before compile time. We call it static. And dynamic, usually we call about the runtime issue. That's how we call it dynamic. It is difficult to overstate the importance of binding time in programming language. So binding time is truly important. In general, early binding times are associated with greater efficiency. It will be faster because you don't need to wait until too late to load the function that you need. Later binding time are associated with greater flexibility. Compiled language tend to have early binding time. Interpreted language tend to have later binding time. Today we talk about the binding of identifier to the variable name. So scope rule, fundamental to all programming languages, is the ability to name data. For example, to refer to data using symbolic identifier rather than the ages. Not all data is names. For example, dynamic storage in C or Pascal is referred by pointer and not a name. So this one actually sometimes is talking about a temporary variable. Sometimes it's called a reference or pointer. That may not have an ID or name to hold it. So here are the four types of the polymorphism. Two main different subcategory. One is ad hoc polymorphism. Ad hoc polymorphism is not by inheritance of hierarchy of classes. So ad hoc polymorphism is like overloading or overriding function. That is one category. In that category, actually, those features are defined when the programmer decided whether it's overloaded or overridden. That's ad hoc polymorphism, decided by programmer. And coercion polymorphism is like casting an object from child class to parent class. That's called universal polymorphism. And there are two other polymorphism. Inclusion polymorphism is a membership. It's a subtype polymorphism. So using the object or number or class, usually these are the inclusion polymorphism. Parametric polymorphism is using generic. Basically, you have the angle bracket with T. Chapter 3, Lecture 2, Lifetime and Storage Management. Lifetime and storage management. Key event in memory management. Creation and destruction of object. Creation and destruction of bindings. What does this mean? This actually means when we try to allocate some memory for some object, you will call A equals new A in Java. So that is a creation of object. And then creation and destruction of a binding. A binding is actually the relationship between these. For example, if I assign this to a certain B, and B actually bind to different memory locations for different objects. But I'm assigning the edges to A, I create a different binding, and deactivate a binding that actually may temporarily be unavailable. Reference to variables, subroutine type, and so on, all of which use bindings. So basically, reference to variable subroutine, for example, a function in Python, actually the functions can be a reference, and that actually also use a certain binding to bind to its function body. And then to a variable, same thing, it's actually need to use a binding. And something like, what is the temporary unavailable? Okay, this actually means that if I have a function, I have f in my main function. So I actually push in my main function's coefficient over here. Some variable being put into here. And then later I call a s function. And inside the s function, actually I have defined this x again. So the original x function in the main function will be overridden, and actually it will be temporarily unavailable until s is return the control back to main, and then it become available again. And the period of time from creation to destruction is called the lifetime of a binding. So basically, when we push some variable into a stack, and then some variable become available, some variable become unavailable, and if we actually push into certain stack, and then some local variable become available here until it pop out, that is the lifetime for the binding. So that we call sometimes that is a functional level local variable. So if the object, our life is binding, so it's actually like a equals new a, right? And then I assign a with b, right? So actually this a assigned with b. So actually this a already been moved to some other places. It pointing to a b object, and then later a assigned with null. So this reference is actually not being used, not binding to anything. And then my object originally I created is still there. It is called a garbage. So that is the kind of garbage need to be collected. And when we actually assign a with null, we can call it as a parking of the reference variable. Parking your car, so it's a parking of the reference variable. And if the binding outlives the object, then it's a dangling reference. What that is means, this actually is a, and then a equals new a, okay. And then actually this a for some reason, I'm sorry, this is in Java, this is not a good example. For example, if we have some array, integer array a in C language, and we use the memory allocate somehow to do that, and then we actually free a later, and that become the memory has already been freezed, and a available probably still there, then actually this is a dangling reference. So that actually means or this a value you copy to another b, but a actually you free a, and that b actually become a dangling reference. That means the body was claimed by somebody else, using the other reference or the other pointer, but the object already been deleted, but the reference or pointer is still there. The textual region of the program in which the binding is active is scope. In addition to talking about scope or binding, we sometimes use the word scope as a non-space cell without a indirect object. So that's the scope. Scope actually is local, global, and functional level, different levels. And we are talking about the levels later. Now let's look at this Java program. So a instance variable is stored in object data, and then a parameter is stored in the runtime call frame, and local variable same thing. And the parameter and the method is stored in the method area, and constant, static constant, a static variable stored in the method area. And it may also have the static object in the method area. So lifetime and storage management, usually this is the so-called memory model. So storage allocation scheme will have static, stack, and heap, three main kind. And the static we call it the method area, and then stack is the for call frames, heap for objects. And static allocation for call globals, static and on variables is preset constants, intern the string, and scalar may be stored in the instructions. Lifetime and the storage management. Central stack is for parameter, local variable, and temporary. And each thread has its own stack, because you need to run the program in parallel or concurrently for some time. Why a stack? Allocate space for recursive routines, and it's not used for Fortran because Fortran has no recursion. And we use space in all programming language. You actually can pop out and then we use the space, memory space, to save memory space. Okay, content of a stack frame, you have the argument, return, local variable, temporaries, and bookkeeping, such as save register, line number, static links, those kind of things. It's called a call frame or stack frame. Local variable and argument are assigned fixed offset from the stack pointer or the frame pointer at compile time. So let's look at a stack frame, or I call it call frame. So this guy is sometimes people call call frame or stack frame, and each function call you will have one frame like this. And typically you have the arguments call the routine, you have the local variable, you have the return ages, you have the bookkeeping and temporary. But actually the frame usually is not organized like this. It's somewhat like if we have a stack like this, certain function S. For this S, usually the lower part will be the parameter, because the parameter copy to here, and then you have the return ages. This one, because that you need to retrieve the return ages later, and then you have a local variable. Why local variable on top of return ages and parameter? Because it will be growing. Because it will be growing when you run each time. Sorry, because it will be growing whenever you have a declare a new variable, it will be growing. So usually the local variable is more, it will be stack up higher and can grow and can shrink. Okay, stack and call frame. Maintenance of stack is the responsibility of calling sequence and subroutine. It's called prologue for calling, and then exiting it is called epilogue. Space is saved by putting as much in the prologue and the epilogue as possible. So when we call a function, it actually costs extra effort and actually it takes more time. So that's why if you do too heavy recursion, your CPU time may be bogged down. And that actually may not be a good practice for you to do programming. And this epilogue and the prologue will actually cost extra effort. So sometimes if it's easy using a for loop can solve problem, it will be better than calling a function, even though both of them will branch out your execution flow from your main execution string. Your execution may be like this, and then you have a for loop, you break out and come back, and then maybe loop several times, right? And you call a function is the same. You jump to some other function call and then come back later and continue your function call, continue your program. But this you have extra effort on the prologue and the epilogue to handle those conference issue. And heap is for dynamic allocation. So you have the constructor, destructor, memory allocate free for different language. There is different, and you actually each time allocate some memory from the heap, and then there may be some area that actually is unused. So we need the garbage collection for the heap. Usually it's something like that. And when we want to collect the data, a garbage bag, it's called a garbage collection. And we need to identify where are the garbage, and then we collect them back to the commonly unused area. So there's an algorithm called mark and sweep. And for right now, we actually don't go into the detail, but the idea is that I scan through my memory and see if there is an unreferenced object that's garbage. I will mark it for the garbage, and later I will claim back this memory and make it unused area. So unused area later I can assign to other objects. And for C language, it's not object; it's actually the used for the memory allocate function. So memory model. I'm going to talk about memory model for different language. For C, C++, we have instruction, that's a call segment, and then we have literal static data, this data segment, and then we have stack area, that's a stack segment. Basically, usually a call process includes instruction segment, data segment, and then your stack segment. Sometimes there is another called extra segment. If you study the operation system, this 4 segment is our process image in your machine. And whatever other language maybe have different memory model, but usually it's actually on top of C frame. And modern monument machine usually is built on C model, C model. And then our static area and constant literal is over here. Whenever you declare a global variable or a static data, and your C language, if you don't declare static, it will be a static. So in C language, static somehow is more like a static variable or private data. Private to the module, and a module is a whole function. And then your heap is used for allocate the memory for different array or string or different structures. And stack is for the call frame. That's the C language model or C++ memory model. The next one is .NET memory model. .NET memory model have the native code and managed and unmanaged code. So for the magical, you can share the CLR services, the Common Language Runtime services. So it's actually similar to the Java virtual machine. And on top of it, you have different language. You compile all to the CLR structure. It's more like a Java virtual machine. So basically, it can provide support for different languages. And Java virtual machine actually by itself can support 200 different languages. And the old day, you have Unmagical that don't rely on the just-in-time compiler. So the C double process a different route to there. So here is the memory model. You have high memory area. You have these different data over there. You have poor process agent space, so the code stack and garbage heap and just-in-time compile code will be here. That's a per process agent space. And there's a system code space. Java virtual machine, we have the heap method area. Method area actually contain the class variable, class function methods, and then we have the per thread. It has you have Java virtual machine stack and the program counter, and in here you have data data area for instant object data and array and strings. JavaScript memory model, Script memory model using the DOM space, the document object model. So your browser has the DOM space. Your window, your document, your phone, and other node actually inside your browser engine, you have a DOM space to accommodate when you download a HTML file, you try to build it as a web page. The web page actually is shown in the browser, and then it's its own DOM space, and not actually it's a object, just work like heap. And then you have the JavaScript engine that actually is for the JavaScript program. So you have the object space, and that is the object inside your Java language created by that. And you also have a separate stack, and these different function and stack will be operated by the event loop. And JavaScript, because it is actually a script language, so it's only one single event loop. Actually, it's not concurrent processing. It's actually just allowing the single thread processing. But here, this one is a JavaScript memory model, and everything is it's only a web engine for the browser. Python memory model, Python is very interesting. So if I use a different way of looking at it, the lower part is actually C language. Upper part is Python. So basically, Python is working on top of C because Python itself is a program. Python interpreter is a program. So whatever you operate on, you are operating on Python, or sometimes people call it Python virtual machine. And you have only some, every Python data is an object. Python program is an object. Python function is an object. And then you have a private heap, and then those object allocator working on it, and there is a raw memory allocator that actually is in C language memory allocation. And then you use a C language interface to operation system. Scope rule number 1. Scope rule, the technical region of a program in which binding is active is called in scope. So we talk about binding, and then we talk about memory model. Now we are going to talk about scope. In most language, with subroutine, we can open a new scope with a subroutine entry, and that is called using the call frame, and then you create binding for the new local variables, and deactivate binding for global objects that are hidden by local object of the same name. And that actually is you either deactivate the global variable, or you actually also deactivate the previous frames, and we declare make reference to the variable. And this actually is the scoping rule for the local variable when you call a method or function. So now we have the dynamic scoping and the static scoping. These two are actually different. And static scoping is local understanding of functional behavior. So you define the scoping at the compile time. And this actually is used for most languages like Java, C++, C#. And dynamic scoping actually is used for very few languages. And it's actually design the scoping at runtime. So where did you get, what is your lifetime of your program available? It should depend on the runtime. So it requires finding a name binding at runtime, and easy to implement. Just keep the global table of state of variable and value binding, but it's actually very hard to understand what it is. Scope rule: on subroutine exit, destroy binding for local variables, reactivate binding for global variables that were deactivated. And I think this is actually the process of creating binding is called elaboration. Actually, is a declaration in some language terminology. So on the exit, you need to destroy the binding for local variables. So you pop out the call frame, and then reactivate the lower function like main function or some function that call the function to be finished. And then you need to restore those global variable or local variables in that call frame. And reference environment, the set of active binding is called current reference environment. So that is your background for its program to run. And reference environment also depends on what we call binding rules. So there is a deep binding and shallow binding. And shallow binding and deep binding are different. Actually depend on where you bind your variable should be bind to where some deeper call frame or a shallower call frame. So scope rule. With static scope rules, a scope is defined in terms of physical structure of a program. The determination of scopes can be made by compiler, and that is more like static scoping. All binding for identifier can be resolved by examining the program. Typically, we choose the most recent active binding made at compile time. Most compile languages like C class code included employ static scope rule. So usually static scope rule is used. Dynamic scope rules are usually encountered in interpreted language, such as early days Lisp. But I think right now very few people actually use this dynamic scope because it's very hard to understand where I get. And if that is an issue, then the language won't be able to become popular. So usually dynamic scoping now is very few implementation now. Static variable in C language. So static, you can declare at the global area, then that will be stored in your data segment.
And if you declare a static variable in a function called label name, this integer actually will be variable static to this function. So whenever this function is called, the same variable n is always the same variable. So for example, a subroutine label can be generated with the L1, L2. If you every time you call this label name and you will print this label with number and the number each time whenever the label function is called, we advance the n by 1. So this function label name will generate L1, L2, and any Ln.
Scope rule number 2. Lecture C5, the nested scope rules. Nested subroutine. The classical example of static scoping rule is the most closely nested rule used block structured language such as Argo 60 Pascal and any other language operators. An identifier is known in the scope in which it is declared, and in each enclosure scope, unless it's declared in an enclosed scope. To resolve a reference to an identifier, we examine the local scope and statically enclosed scope until a binding is found. This actually is very wordy. And then let's look at the example on the right. So from the green, C is local to here, and D we have no definition, so we look into some higher definition from this here. There is no definition for D, so this D is actually local to here. And then we have the print B, and then this print B actually you've got B equals file, right? B equal 2, so this B actually is local B over here is equal to, and the D you actually here, this one is the same as this one as 4. Since it happened to be here, it actually is the same for this one. And then C is defined local to this green, so C won't be available in here for the green one. And A is global, so A is here. And then if A is 1, we go into here. And B is local to here, so this B is not this B. It's actually nil. So that actually kind of bizarre anyway. Let's look at this scope rule. So a name to object binding that is hidden by a nested declaration of the same name is said to have a hole in the scope. So right here, for our A, that's a parameter for procedure 1. Procedure 1 started from here to the end of here. The body is over here. So A, the lifetime would be here to here. The scope is the whole bar. For X variable, it's local to P1, so it's up to here, and P2 that is part of it, so you go into here. And then in F5, X is actually declared locally. So this one is different from this one. So X is actually not in power until F1 is finished. Other than that, all X are belonging to this X over here in P1. For P2 is a procedure for P1, so in all of the domain for P1, we'll be able to see P2. So P2 is whole bar. For A2 is a parameter for P2, so when P2 is alive, it will be alive. So P2 is actually, let me see. P2 is alive from here to here, so A2 is up to here. P3 is a P2 procedure, so it's also alive in P2 domain. A3 is parameter for P3, so it's in A3's domain, P3's domain.
P4 is a procedure inside the P1, so it also has a whole bar. Anywhere in P1 will be valid scope for P4. A4 is parameter for P4, so actually lifetime is the whole P4 procedure. F1 is a subfunction for P4, so it also alive. The scope is also the whole P4 range. Parameter A5 is actually a parameter for function F1, so it will be in the F1 scope. X1, at least inner X is a variable that is valid for F1 scope, so it will be alive when F1 is alive. So that's the way we actually define the nested scope usually. And then, for example, in X, there is a hole, and there is an extra definition for local variable. We call that is a hole for the scope. So my procedure.x, for example, refer to the declaration of x in subroutine my procedure, regardless whether some other x have been declared in lexical closure scope or not. In C++, which does not allow subroutine to nest, we use the specifier double column for x. Refer to a global declaration of x. Scope rule will see classes a relative of modules later when discussing abstraction and object-oriented programming. These have been have even more sophisticated scope rule. Include is an example of language with lexical nested scope, in which all scopes are closed. Rules designed to avoid areas which complicate optimization occurrence of arguments. Note that the binding is created in a subroutine are destroyed when subroutine exit. The module or modular either give you close the scope without the limited lifetime. Binding to variable declared in the module is inactive outside the module. So this is the scope for loads a local variable to a module. The same sort of effect can be achieved in many languages with on or static in C term. Access to non-local variable static link. Each frame points to the frame of the routine inside which it was declared. In the absence of formal subroutine, correct means closest to the top of the stack. You access a variable in a scope K level out by following K static links, and then using the known effect within the frame thus found. So this one is when you need to access some local variable and you want to use the static link, you kind of can do that. So local access local variable, basically you need to have a frame register and then use that frame register using the relative data displacement or the relative address, and then to find the local variables. So access to local variable. Here are some scope. So the simplest way in which to find a frame of surrounding scope is to maintain steady link. So basically, I have if I have A equal B, B equal C and D, and then E. So C and D will refer to B by steady link. So it actually keep the frame to pointer to the parent frame. So it will create some surrounding background, and B and E will be linked to A or A to have the relative access to the variables.
Scope rule number 3. Scope rule in a block. Declaration order. Declaration order in several early languages, including Argo-60, Lisp, required all declarations appear at the beginning of their scope. Pascal modified the requirement that name must be declared before use. Pascal retained the notion of the scope. Retained the notion that the scope of the declaration is the surrounding block. So basically, if you declare a n right here, and the scope will be the green part, and if you declare a m, it will be in this blue one. So n equals 10, and this n will be assigned to m, and later m equals 20. So the problem here is this n is local to be here, and then this n is supposed to be this n equals 20 according to this scope rule. And there's a conflict between this n and this n. So there's a static semantic error. And if we look at the Java or C++, basically we will see the n order, the declaration order will no longer be a problem. You will basically base on the block size to determine the scope power. And for a single variable, it will be at the scope definition size. So there will not be a problem. If in Java's case, this n will be a 10, if it is a global variable. If we redefine it, and there will be a conflict, and the compiler will pick up. And if there is no such conflict, then the n will be 20. But in Pascal, these do create trouble and will complain a static semantic error. So declaration order, Pascal says that the second declaration of n covers all full function. So the semantic analyzer should complain on the line 5 that n is being used before its declaration. The error had the potential to be highly confusing, particularly if the programmer meant to use the outer n, that n equals 10. So something like this will create a semantic error. So here, the 2n actually has conflict. In order to determine the validity of any declaration that appear to use a name from a surrounding scope, a Pascal compiler must scan the remainder of the scope's declaration to see if the name is hidden. Declaration order. Most languages after Pascal, to avoid this complication, most Pascal's successor, including C or other language, the scope of an identifier is not the entire block in which it is declared, but rather the portion of the block from the declaration to the end. So this makes things better. So if we have a block like here, I will start to a scope from the declaration statement to the end. But the parametric part will cover the whole method from in the green one over here. And if it is defined in the catch block for the catch block handler, the exception handler, that would be covering the whole catch block. If our program's fragment have been written in Ada, for example, or in C, C++, or Java, no semantic error would be reported. The declaration of M would refer to the first outer declaration of N. C++ and Java further relax the rules by dispensing with the define before use requirement in many cases. In both languages, members of a class are visible inside all of the class methods. In Java, classes themselves can be declared in any order. So basically, it will become you will have the outer of the declaration will all be accepted, especially for classes. But if individual variable like primitive data type, it
it will actually matter where it is declared, especially in the local blocks, such as in the function. But outside the function, for the instance variable, it doesn't matter. And the method order, it also doesn't matter. Whole block scope for C#. C# return to the particle notion of whole block scope. The following is embedded in C#. So here, if you declare an outside and then declare these two will have conflict. But I don't think that this whole block idea is a good idea. We should go to some language that actually supporting the out of order declaration or inline declaration. Declaration order in scheme. In the interest of flexibility, modern Lisp dialect tend to provide several options for declaration order. In scheme, for example, the lat rec and the lat start construct define the scope with respectively whole block and declare to the end of the block, declaration to the end of block. Semantics. So these actually two. One is providing you the whole block. The other one is just define the declaration to the end of the block semantic. The most frequently used construct that provides yet another option. So here we assign A to 1. That's outer scope is this lat. So it covered from here to the end of here. And that another one inner scope, we define lat from here to here. So this A1 is very for the whole block, including the lat statement. But this A2 definition only cover this inside. So with the B defined to A, and then when we return B value, the next declaration of A and B doesn't take effect until after the end of the declaration list. So we bind 2 to A and A to B. This is a binding list. So in fact, this A is this A, not this one. It's binding list, but need to happen on somewhere else. Like here, maybe okay, but not in the binding location. So this one actually is bind to 1, and B is bind to 1, and then B bind to A, and then A is 1, so B will return 1. Declaration and definition. Recursive type and subroutine introduce a problem for languages that require names to be declared before they can be used. How can two declarations each appear before the other? C and C++ handle the problem by distinguishing between the declaration of an object and its definition. A declaration introduced a name and indicates its scope, but may omit certain implementation details. A definition describes the object is in sufficient detail for the compiler to determine its implementation. If a declaration is not complete enough to be a definition, then a separate definition must appear somewhere else in the scope. So here, recursive type subroutine introduce a problem for language that require name to be declared before they can be used. So this actually resolving the ambiguity. C++ handle the problem by distinguishing between the declaration of object and its definition. And so here is talking about what is definition, what is memory allocation, and like C or C++, they handle well because the declaration is a declaration. You make the variable for certain type. And the definition is definition. You actually assign some subject or binding into there. So that actually is a good, distinguishing effort to make the declaration and definition separate. Declaration and definition in C. On the left-hand side, we have structure manager, and we have employee, and employee has a boss and next employee pointer, so it actually can be used for linked list. And then the manager, it has a employee pointer for first employee. So the manager student will manage a whole team of employees, and that will be in the linked list format. And each employee will point it back to boss as well. So initial declaration of manager need only to introduce a name. So this one actually is for declaration only. It doesn't have the implementation. For the implementation is later. So this one is sometimes called just like prototype. So that people knows that manager is a struct type. And then what kind of struct type it will be defined later. So here it just declare a manager pointer of the both data field. So on the right hand side, we have a prototype for list tail. Again, this one is only for declaration, but later we have the definition down here. So here you may call it, but you just need to know what type of variable this is. It actually is a function reference, and then there is a parameter of the follow set type, and then that's it. That's the only thing you need to know when you want to code it. You need to know about the function name, and also you need to know about the parameter type. That's the only thing you need to know when you actually call a function. So prototype is good for C language to make it make the other function know about it. But this actually is lifted. The requirement of this is lifted in C++ and Java. Actually, we can afford the out of order declaration, but C++ is not that clean. Java, on comparison, is a better defined language. Nested block. Variable declared in the nested blocks can be very useful as, for example, the following SQL. So here, temp only is available within this block. So the curly braces in Java or C, you don't need to have a for loop header or while loop header or a function to use this. It is okay you actually put a curly brace pair and put some code inside here. It just create a local domain for this integer temp. And this integer temp will be valid after its declaration. So actually this is called a code block. But code block create a scope for certain variable that declare inside there. And if you add a if statement, that will be a decision block. If you add a while loop header, it will become a while loop. Scope rule number 4, module, class, and dynamic scoping. So let's look at this module. Module has several names in different languages. Help software development in parallel by a team of engineers. So modularization of effort depends critically on the notion of information hiding. So module is trying to make sure that it hides the details from the programmer, but it will reveal some part that is visible to the programmer, make the programmer have enough knowledge to do programming, which make object and algorithm invisible whenever possible. The portion of the system that does not need them. So this actually provides some sort of encapsulation of data and subroutines. It is information hiding by subroutine actually is limited. Static variable in subroutine allow programmer to achieve information hiding for a single subroutine. And here actually say the module for information hiding by subroutine is limited, but because it's not as good as the class. Class provide the private data field, and module is just create certain namespace or domain or scope. So it's actually still different from the so-called class. The module construct can help achieve this goal. So let's look at the module here. Module as object. A module allows collection of objects, subroutine variable types, and to be encapsulated in such a way that objects inside are visible to each other, but objects on the inside are not visible to the outside unless explicitly exported or used. In many languages, objects outside are not visible on the inside unless it explicitly imported. Import and export convention vary significantly from one language to another. So basically, there is no simple way of declaring this. Some language call import, export, some language call using or use. But in all cases, only the visibility of the object is affected. Module does not affect the lifetime of the object they contain. So in C++ language, actually it's called namespace. Using namespace, we can have class, global variables, functions under one name. We can change the global scope to subscope. So we may have different subscope under the namespace. Namespace is a logical compartment. So basically, namespace is just a compartment. It's kind of a box. You put something into the box, and to avoid naming collision. So outside the box, inside the box, we can only make things visible within the namespace. So if you use certain namespace, it will be open for you. The naming conflict and the collision always may occur when some program is using more than one library with several variables and all functions having the same name. The name collision may occur for global variable, global function, classes, etc. Default namespace is global namespace and can access global data and functions by providing the double column operator as a separate specifier. We can create our own namespace, and anything declared within namespace has scope limited to the namespace. Module as abstraction. Pseudo random number generator in C++. So here is a namespace. So in C++, actually namespace is the module. So here, if you don't look at this, it's quite similar to a class. But actually you have the data, you have a function, and it's similar to any class. It just have the module variable, module constant, and module methods. And in order to use that, you have special way to access the module by using this namespace. Otherwise, you need to use the specifier, the double column, to access the data and the function inside here. This module would typically be placed in its own file and then imported whenever it is needed in C++ program. Bindings of name made inside the namespace may partially or totally hidden on the outside, but not destroyed. In C++, where namespaces can appear only at the outmost level of lexical nesting, integer seed will retain its value throughout the execution of the program, even though it is visible only to such seed and random integer. So basically, these different variables will be unconstant, will only be visible by the function over here. We have the seed is used over here. We have seed over here. We have m over here. And this m actually is I believe is a prime number. So you use this prime number and take a modular to provide the random number. And that's the way we do work on it. Actually finding the prime number to generate the random number. That's a technique. And here is unlike the class, there is no such thing as constructor. but we actually group the data and method together into a module, and in a module in C++ is named namespace. Module as abstraction. So outside the random mod namespace, C++ allows set seed and set integer to be accessed using the specifier. So you put the module name on the namespace name, and then double column with the function. So we can call this. So we can use using this or using the whole module. If we use the whole module, we will just call the we will call this set seed and random int function, and then we don't need a specifier if we use a namespace like this. So using the namespace means whenever I see a set seed will be interpreted as by this version. But if there is another namespace called, say, readMod2, then those functions, even though they might be set seed and random integer, it will not be used. But if you use the version from readMod2, then you can use the namespace readMod2 as well. So you can actually switch. So compare this and this. The one using the single function part, and then we compare with this using namespace. Using namespace will use more memory because it pull all of the name over to your program. But actually, if you using the random mod and then with the function name only with the specifier, it only allow you to use that particular function, but not all the function and data in that module. Import and export. Some language allow the programmer to specify that names exported from modules be usable only in a restricted way. Variables may be exported read-only. Variables of that type may be declared, passed as argument, and possibly compared or assigned to one another, but not manipulated in other way. A module that names must be explicitly imported into it is called closed scope. Language with a closed scope, like Modula 3 Haskell, a module that does not require imports are called to be open scope. Language with selective open module is C++, Ada, Java, C++, C#, and Python. For example, in Java, the mass function, the mass.random or mass.abs absolute value, you actually don't need to import, and you just use the class name, and then you can use that class name, that function. That is called the open module, but actually it's only limited. Not every function or module can be ported in that way. Using import and using directive is a common option now in many different languages. Module as manager. And first we need to know what is a manager. Module facilitate the construct of abstraction by allowing data to be made private to the subroutine that use them. One used as figure 3.6. However, each module defines a single abstraction. Continuing our previous example, there are times when it may be desirable to have more than one pseudo-random number generator, and in that case, it's just like a class, but we call it manager. Manager module is a namespace. Namespace means module, and then you provide a structure, and that structure actually has a constructor, and we call it the create function. But create function actually return the pointer of the generator type. So effectively, it works like a constructor. So in fact, this manager module just works like a class. You have the constant data field over here. You have the data structure just like object or your instance variables. You have a function creator. It works just like a constructor, and you will return the desired structure type for you, even though this is not called object, it's called a structure. And then you can actually generate a structure and then return the pointer to that structure as a return, and that effectively work like a constructor. And then we can have a function like member methods, and over here. So basically, this manager module for pseudo number generator in C++ works just like a class, and we call this a manager module. So module types compare with class. So left hand side is module. It's written in C language, .h file. I'm sorry, C++ language. You have time.h, and you use the random mark manager module. And the right hand side, you have the class. So as you can see, using the class still be more concise, actually more compact compared to a module. So that's why nowadays fewer people are using the module compared to the classes. Classes actually is a better way language construct, because it officially modularizes your data and providing the public and the private access visibility modifier. So it actually provides you better control on the data compared to the manager module type. Dynamic scoping. In a language with dynamic scoping, the binding between name and object depend on the flow of control at runtime, and in particular on the order in which subroutines are called. In comparison to these static scope rules, dynamic scope rules are generally quite simple. The current binding for a given name is the one encountered most recently during execution and not yet destroyed by returning from the scope. So here we introduce the idea of dynamic scoping, and some language implement this, and not in our Java or C++. Let's look at it. So here is a comparison for static and dynamic scoping. So consider the figure 3.9. If static scoping is in power, let's use the idea of scoping in C language to look at it. So we declare a global variable called n, and then as n assigned to, and then we read integer, so we call the read integer, and then it read in some integer, and then we call the second function. So second function is here. We declare a local variable integer, and then we call first. And then when we call first, this first function will have the n function, and n function supposed to have the global definition over here. If we are using the static scoping, so in that case, in the second function, the first function and the n in second function actually is local, so it doesn't affect first. So we call it and set n to 1, and eventually we write that 1 out. So for static, it's actually will be printing out 1. And for dynamic in power, actually we run this n equals 2 and read integer, and then we run second function, and then we define the n integer, and then after that we call 1, and in that time the recently called scoping will be empowered. Then n actually modify the local variable in second function. So outside the second function here, the n will be the same n without modification, and go to the right integer function, and you will print out 2. So that dynamic scoping, if it is empowered, actually it will write out 2 in this situation. So what is good for dynamic scoping? For implementation, it may be better because you will be using the recent definition of n. As long as you keep track of a global name table, it should be fine. But for understanding of the program, it actually will be more difficult. So runtime error with dynamic scoping. Which dynamic scoping error associated with the reference environment may not be detected until runtime. Figure 3.10, for example, the declaration of local variable maximum score in procedure foo accidentally redefined the global variable used by function scale score, which is then called foo. So here we have a maximum score integer, and then we have foo function procedure and the function define globally, and that actually will actually have used the maximum score times 100. I'm sorry, raw score divided by maximum score and then times 100. So it's a percentage score. And the declaration of the local variable maximum score in the full subroutine, it is redefined of the global variable. But for static scoping, it will be only empowered for full function. But dynamic, it may affect the one that call later. So actually, this one after definition, if you call it scale score, it will be modified. So since the global is maximum score is an integer, local maximum score is a floating point number, dynamic semantic check in at least one language, in some language, will result in type class message at runtime. If the local max score have been an integer, for example, if here you declare it's an integer, then dynamic scoping will have no error, and the program will almost certainly produce an incorrect result or undesired result. So that when you use the dynamic scoping, where you define it is actually make a lot of difference. Be careful for those dynamic scoping languages. So now let's talk about lecture A, meaning of name within a scope. So the level of the local locality in your program will have built-in global enclosure and local. And built-in is language design time. You will define the scoping, and then global is program doing time. So global variable is a global variable that defined by user. Built-in variable is a variable that may be defined in certain package, but is determined at the language design time. Some of these variables, just like Java's integer that mean value or integer that max value, those variables, even though they are constants, but let's consider that it's also a ID and a variable, and actually is defined at the language development time. And we have the enclosure that actually may be in certain function or certain class. So it will be empowered at the loading time if it is a class. And then for local data field, it actually will be empowered when the function is called. So that is a different level. So basically, we have a class. We have certain function main. And over here we have this local. And enclosure is a bigger scope. For example, a certain class that encloses it, or certain block that code it, you have the enclosure. That's loading time. And then global, you have some global defined here for constants or something. And build time is before this class even be created. So a name is a numeric character string representing something else. X, sign, F, program 1, null are names. Is that names? Some of them are literal, like null, and some of them are name. 1, 2, 3 tests are not names. These are literals. Null is a name, and it usually means a certain specific value. Plus less than equal to may be name, and if they are not built-in operator, it depends on the language. Binding is an association between two entities, name and memory location, or name with the function. Typically, a binding is between a name and the object it refers to. So basically, binding is here, and we have the dynamic binding, and also we have static binding that is depending on whether there is a polymorphism or not. A reference variable is a complete set of binding active at a certain point of the program. And then the power of the binding is when the binding is in power, we call it the time. The lifetime is called scope. And scope is a region of the program or time interval in the program execution during which the binding is in power. And the scope can have dynamic scoping and static scoping as well. A scope is a maximum region of the program where no binding are destroyed. So on the right-hand side, we may have an object. It may have a name called my object. And then you can create a pointer that you put a star in front of the pointer and declare my class. So that pointer is an indirect accessing using the address to access the object. And then you will create the my class, my object, and become a reference or alias for this my object. So the pointer can use the body, the star, and then my pointer, and it's the dereferencing for that my pointer, and then you will get the body. And if you put the address sign for the my object, the reference, and it will become a reference, and then it can be assigned to the pointer data field. So the meaning of the name within a scope, two or more names that refer to a same object at the same point in the program is said to be alias. So alias is like different names. So somebody has a name, has a nickname, has a sweetheart name or something, any kind of name that defined for a certain same entity or object is called alias. A name that can refer to more than one object at a given point in the program is said to be overloaded. So name can be used for different objects or functions. We call it overloaded. So this one is same reference, different object. We can refer to different objects. And the definition of a name is called overriding. That actually redirect the name to a different entity. Overloading is related to more general subject of polymorphism, which allow a subroutine or other program fragment to behave in different way depending on the type of its argument. So it's also a kind of polymorphism, but overloading is static binding. Overriding is dynamic binding. And overloading is by type matching or inferring. Alias. What is alias good for? Space will be safe. Modern data collection methods are better. Multiple representation union variant are better. Pointer-based data structure, linked data structure, different way of traversal. And these can be different aliasing. Call by reference in C++. With the aliasing, it provides the input and output capability for a variable. For example, here we have accumulate alias, double alias x. X is an alias for the variable that put in. So this x variable become a input and output variable for the function. So right here, if we have sum equals sum plus sum, and sum equals 2 times sum, the old sum, and then sum of the square plus equals 2 times the old sum square, something like that. Let's look at the example. So here, for example, I accumulate sum. So sum we put here, and then we have the x over there, the sum with sum, and then sum of square plus equals this. This is called by reference. And the x here, the x will be updated. So x will mean this outside x. Okay, so this sum and this sum actually will be the same, and even the x is the same. So basically, if I pass pass the sum over here, and sum contain a 2 over here, so this x will be pointing to the same sum. So x will get 2, and then original sum equals the original sum 2 plus 2. You got 2 times the old sum, that will become 4. That's 4 will be stored here. And because x is pointing to the same sum, so x become 4 times 4. And then you put then the sum of square, the value will be increased by 16. Something like that. Okay. Alias and code improvement. So here we have the pointer P and Q, and then we assign the body of P to A. So we copy the body of P to A, and then we just copy the 3 to the body of B, Q, and that body of Q is actually body of Q. Okay, we assign 3 over here, and then we copy the body of P to B. So we have 3 action. One, we copy the body of P to A, and then we copy 3 to Q, body of Q, and then we copy the body of P to B. 3 operation. Overloading. Some overloading happen in almost all language. Integer plus and real plus, and even the concatenation of string are considered overloading for the plus sign. And read and write in Pascal, function return in Pascal, they are overridden. Some language overloaded, Some languages get into overloading in the big way, just such as the Ada and C++ languages. Overloading and overriding function. Overloading function, 2 different things with the same name in C++. Overloaded norm, such as norm of integer and complex. These are 2 different data type, but operated with the same function name, but the definitions that will definitely be different. Polymorphic method, one thing that works for more than one way. Actually, for example, the minimum of certain things in one modular 2, you can work for a certain class in one way and in another class for different way. Generic function module is a syntactic template that can be instantiated in more than one way at compile time. In C++, you can use the macro, or C language you can use macro, and in C++ you can use template. In Java you can use the angle bracket with the generic type matching. Overloading or enumeration constant data. So here I have a month defined as this, and then we have the print base with the decimal binary, octal and hexadecimal. And then octal will be overloaded for months and print base. So when we refer to octal or October, it will be the same name. So here we have this, and then we assign December to months, and then octal to print base. Okay, and then print out octal. What is this octal? So we don't know. So we better use a certain reference way to actually resolve the problem. That's the overloading of enumeration constant in Ada. Overloading of built-in operator. It is one of the many exciting features of C++. Important techniques that have enhanced the power of extensibility of C++ is to overloading the standard built-in operator. In Python, actually, there are a lot of magic functions. The double underline function, those magic functions are also a overloading feature for C++ and Python language. And here we have the operator plus that will override the plus sign for the complex data type. Binding of reference environment. Number 1, binding. Binding of reference environment. The reference environment of a statement is the collection of all names that are visible in the statement. Static scope rules specify that the referencing environment depends on the lexical nesting of program blocks in which names are declared. Dynamic scoping rule specify that the referencing environment depends on the order in which the declarations are encountered at runtime. So basically, what we mean by referencing environment is all of the binding existing for the current execution environment. So A variable, B pointer to an object, something like that. And these are the whole thing is called reference environment. So it's a statement of the collection of all names that are visible in that statement. And dynamic scoping rule specify that the reference environment depends on the order of the declaration. So basically, dynamic scoping happens when you actually call to some other subroutine node then, and then those A, B may be actually specified at a certain time, and then at the runtime you decided the variable is bind to a certain number. And static is at the compile time based on the hierarchy of the calling structure. So that actually maintaining of the reference environment fully depend on the scoping rules. So deep and shallow binding. Deep and shallow binding actually is used before. And let's look at the example. And here we have a print selected record. Print selected record would have input for database, predicate, print routine. So right here we have the main program. We have setting the threshold for 35. And then 35 is the number of person that actually the age need to, 35 is a threshold for the age for a person. So each person's age greater than 35, that is the this Boolean functions result. So print selected people, then we would like to use the people. People is the database. And then older than 35, that is the predicate we put in here. And then print function is a print routine for print person. That is the routine. So we use these three things put into the print selected record. And then print selected record function will decide the integer line length. A line length, if the device standard output is terminal, the line length would be 80 character. And then if not, it would be 130. What that really means. And at all time, a single print device, say like a monitor that I have right now. In the old day, like we have the monochrome computer, each screen has only 80 character. And then if you print out a file to a printer or a file, you can do 132 for the Parametric printer. So this actually is very old stuff, and you will adjust based on the runtime print person's setting. So you will adjust for the printer hardware to get the right version of line length for this checking the device type. And then for each record R in DB, we actually print if the predicate check this print person's age older than threshold Boolean function. And then if the guy is actually older than 35, we'll print that with the print person function. So this one here in a language with dynamic swapping, it's natural that for procedure print selected record to declare and initialize this variable, the print person variable, locally, knowing that the code print routine will pick up if necessary, if needed. For this coding technique to work, the reference environment of print routine must not be created until the routine is actually called by print selected record. So this one you cannot pre-decide okay, which function I will call, because you really need to actually check the device for the variable length. Otherwise, you will not pick up the right routine. So the late binding to the referencing environment is of a subroutine have been passed as a parameter is non-shadow binding. So this one is a shadow binding, and actually is usually default in the language with dynamic binding. So here we utilize the shadow binding and the dynamic binding because this one is not deeply bind with some call hierarchy. Here actually you just check the current device and then get the print routine to work. And this print routine may have different version for the device of 80 character or 132 character width. Okay, right here. And for function older than threshold, by contrast, allowing binding may not work. Shadow binding may not work. For example, the procedures print select record happen to have a local variable threshold. For example, here it actually has a local variable called threshold. Somehow in here, then the variable set by the main function influence the behavior of older than threshold will not be visible when the function finally called, and the predicate will be unlikely to work correctly. In such a situation, the code that originally passed to the function as a parameter as a particular reference environment in mind, it does not want to the routine to be called in any other environment. So here we want it to bind to the threshold that we called it, not the local this threshold here, but we want it to be bind to the one we actually called it in another environment. So this is actually deep binding, and because it's deep binding and actually also dynamic binding. Subroutine closure. If your language lets you store subroutine as a value, closure actually is just like passing your function name as a parameter or a pointer. So if your language lets you store subroutine as value or nested subroutines, then you can make closure. So basic closure usually is a lambda expression or a function name as a pointer, usually C language, C++ language, or the interface in Java language can be used as the function closure or parameter to be used. Deep binding environment is implemented by creating an explicit representation of a reference environment and bundle it together with a reference to the subroutine. The bundle as a whole is referred to as a closure. So basically, closure means that you pass the subroutine as a parameter and usually is in a referencing environment. So subroutine closure right here, we have this a function, and a function being called, you pass 1 and c over. And then this one, I is 1, p is c. P is a pretty function. So actually the function c is passed. And then a's body is right here. The defined function is fine. And then a's body is over here. If I right now is 1, greater than 1, we call this, otherwise we call A2 and B. So actually we pass 1C over here, and then it will call 2 and B. And then B function will print I, but now the problem is that whether this I is 2 or 1. It depends on whether you shallow bind it to 2 or deep bind to 1. Deep binding means the lower level binding. So for deep binding, actually it will go 1, because this one actually is the level that defined it. Your local parameter define the function. At that time, you bind it to here, that is actually 1. If you bind to the runtime dynamic binding and then bind to this 2, the pass is the body that call this guy, and that actually shallow binding will be the I2. So for Python language, it's using the deep binding idea. So for Python environment, use will print out 1. But if shallow binding is used, it will print out 2. So the result of a deep binding .py, we have the same program showing here, and then it will print out 1 as deep binding. And binding of reference environment, number 2, closure and lambda expression. First class value and the unlimited event. A value in the programming language is said to have a first class status if it can be passed as a parameter, returned from subroutine, and assigned to a variable. Something that you can do as a parameter, that's the beginning of a function, return, that's the end of the function, and then assigned to a variable that actually put as a right-hand side value. With these 3 large feature, that value is called the first class value. And actually this one is now a lot of languages just implement the first class variable. Second class variable is that you can pass, but you cannot return. That is second class. Third class is that you cannot pass, you cannot return, and you can only be a right-hand side value. So that's usually a label that's called third class. So here are the definition of first class value, second class value, third class value. First class is that you are writing a first class seat in airplane, so you can do everything what you want, using whatever toilet you want to go to, or getting the high class service from the waitress, air stewardess. And then if you are second class, maybe you are limited with some feature. So return first class subroutine in scheme. So here we have an example of returning this first class subroutine scheme. So here we have a binding that the function f as the plus dash x2. So we actually this one plus x is defined as a lambda expression. So this one we pass 2. 2 is the x over here. So plus x actually is a lambda y plus 2 and y. So this plus 2 actually defined as lambda y and plus 2y, this expression. Then that's the first definition. And then this one we again put the f3, so 3 bind to y, because the lambda expression being bind to the f, and f have a 3 binding to there, so f3 actually bind lambda 3 and 2, and y actually is 3, so you actually will return 5. So let's define this. So here, if you look at the define plus, and I use the green color. So here the B expression is green color up to here, and then red color is the inner gray color. So F3 is bind to the red color lambda, and the this second level outer layer lambda is binding to B as green color, and outside define plus X is actually outside F function at plus X function. So right here, what will happen is like plus 2 is 2 and return value enum to here, and then enum y is 3. So you bind that 3 with the plus 2 function. So that's the construct line 4 through F and then calling plus X with argument 2. The function plus X is defined as line 1 here. It returns the unnamed function declared at the line 2, but the function referred to the parameter X of plus X. When F is called at line 5, the referencing environment will include X in plus X, despite the fact that plus X has already returned. So somehow we must ensure that X remains available. So the same closure, we can write it in Java format. If we use this interface in function, an interface in function has a function call, a method call. And method call is implement here. So similar to the lambda expression in scheme, we have a plus 2. So plus 2 is actually we put the 2 into this here. So n is set to x, so the x inside here is actually 2. So that is the same setting of 2 for the. So this call is actually the y lambda, and then here plus x for the x lambda. So when your y lambda, you pass call 3. Here I is actually the y in the y lambda. So you print 5. And for C double plus, similarly, we have a class because C double plus don't have the interface. So we use a abstract function in the class. So this one is actually a abstract class. But in C double same they don't have a name for abstract class. As long as you have a virtual function and set to 0, this equals 0 will set this function as an abstract function. That means it have no implementation. And this one is a virtual function, so this interface need to be implemented. It's just like an abstract class, and then it is inherited by plus X. So plus X inherited this, just like the plus X here implement this in function. So that is a extension. And then you actually, when you call, you put a 2 there, and then plus X actually will be setting the X to 2. So here X is 2. So this one operator one is like the green lambda. I'm sorry, this is like a white red lambda, and plus X like the green lambda. So 2 actually setting 2, this n to 2 for X, that is setting the green lambda, and F3 is the red lambda, and then you will print out 5 as well. So here we have Java, C double plus, and scheme for the same function of the object closure. So object closure, we have C#. C# uses the delegates. So again, here it has a plus 2 function, and then there is a delegate of function. Use this function as a delegate for the new int, and then the console write F3. So F3, this one is a print function. So F3 actually will pass this into an in function, and in function actually is defined over here. And then we have plus X. So when we have this in function equals this, and we put a plus 2 call, so this one is the green lambda, and actually this one will pass the call function into the plus 2 here. We let me see, it will pass this function to the in function here, the result value for here, and that value will be put in here. So you will call this one with 2 into there, and this one with the G of 3 you print out 5, and this one actually using the delegate, and this one using a some sort of class closure, it will also print out file. This is similar to Java case. And this one is a special data case for C#. So data case and unlimited extent. Here is C#'s special feature. C# does not permit subroutine to nest in general case. Version 2 of the language allow data case to be instantiated inline from anonymous function. This allows us to mimic the call or scheme. So here we can set this up and then use a data case. And this data case is just like a lambda expression. So lambda expression for the various language scheme or Camel, Ruby, and C#. Actually, you can look at the grammar, but in fact, all of these are the same. So we won't go into the details right here. So a lambda expression in C++, we have capture of the clause equals, that is assignment by called by value, and then parameter s. So here is an s, and mutable and throw integer. So here, when you have a lambda expression, you put a 2 in there, and the 2 will be assigned here, and then you actually will return n, and n actually is whatever y value you call, and then you will return n. So this one is the same function written in C++ 11 version. So lambda expression can be used like here. We have the lambda expression. We have no capture. When you have empty capture, it means that one has no external reference. So basically right here, you actually will have an E. So for each V as a vector set, the begin vector and the end of the vector set, and it will check whatever element will be put here, and then if it is less than 50, we'll print that element out. So this is a simple lambda, and then there is no specification for the called by reference or called by value. Equal is called by value, h sign is called by reference. So lambda expression, you have different way of calling it. Here is a lambda expression for Java. You have an argument list, and then arrow, and then body. The argument list, actually you will have x and y. So you actually can have like s assigned to s and then call s length. Okay, the formal parameter of the lambda expression may have either inferred or declare type. So something like this, if we can have no parameter and just directly return 42, that's a function. So here is a parameter, and the second part is the return value. Parameter and return part over here. So lambda expression in Java, for example, if we want to have array sort, we can have a new age comparator. And that actually can be defined as a lambda expression like this. This whole thing can be replaced by this lambda expression. Name in compilation process. The C++ compilation process, you start with the .cpp or .h file, and then you pass it into preprocessor and then compile to object code, and then you actually link and load into your memory and run it. So you have a source code of .c file or .cpp file, and then pass through the compiler, and you have a .o file or .s assembly file, and then assembly file you need to assemble it, but if it is object file, you can dig it and run. And separate compilation, you can provide the object code from different language and then link them together to run. So the macro part, this one is for C language, and this is all we will pass this section. It's not actually commonly used now for this. It's just a preprocessor. Separate compilation. Rule for how variables work with separate compilation are messy. Languages have been jury-rigged to match the behavior of the linker. So static on function or variable outside a function mean it is usable only in the current source file. That's global variable. But if you want to share it, you need to put extern. So extern actually is a public. If you think about in Java's language, it's actually a public variable or public function. And static is actually private. So it's only usable for the same module. And the static is different from the static inside a function. Inside a function, that variable is static to the function, not to the module. Separate compilation, separately compiled file in C. The extern on a variable or a function means that it is declared in another source file. So it's like a imported variable, and it is really public. Function header without body are external by default. So functions are external by default. So functions are public, but variables are static by default. So basically, C language, even though they have no idea of the encapsulation or object-oriented programming, but it do have the static for the private data and then external for function, public function. So it's somehow like encapsulation to have private data, public function. Conclusion, the moral of the story. Language features can be surprisingly subtle. Designing language to make file easier for the compiler writer can be a good thing. So don't over-design the language so that the compiler writer cannot implement it. Most of the languages that are easy to understand are easy to compile. And if it is not easy to understand, it's not easy to compile and not easy to use as well. A language that is easy to compile often leads to a language that is easy to understand. More good compiler on more machines, better, faster code, fewer compilation bugs, smaller, cheaper, faster compiler, and better diagnostic. So always keep things lean, keep things easy to compile, and keep things easy for developer to use. Thank you. Bye now.